You ever wonder how a simple Hello World program actually, shows up on your screen? Or how your code can pull a file from your hard drive? Well, there's this powerful, kind of invisible thing happening in the background. And today we are going to pull back the curtain. All right, let's dive into the world of system calls, your code's one and only gateway to the computer's core.
So here's the game plan for this explainer. First, we're going to talk about the two separate worlds living inside your computer. Then we'll introduce the bridge that connects them, system calls. We'll check out the huge menu of services they offer, and then we'll really zoom in on the famous fork call to see one in action. After that, we'll wrap up with why this whole system is just so incredibly important. Okay, so let's kick things off with a big problem here. Your apps, they need to access hardware, the screen, the disk, the network. But just imagine, what if every single app on your phone had direct, uncontrolled access to your camera or microphone? I mean, one buggy app could just create total chaos, or even worse, crash your entire phone. Total disaster, right?
Seriously, think about it. When you write a line of code that's supposed to print something, you're not telling the individual pixels on your monitor what to do. Your code lives in this nice, protected little bubble. So how does it get its message out to the real world, to the physical hardware? To figure that out, we've got to understand the two modes of operation.
This separation of power, it's everything. On one side, you've got user mode. This is kind of like the sandbox where all your applications live. Your browser, your games, your code editor, they have very limited, very restricted access. But on the other side, you have kernel mode. You can think of this as the castle's control room. This is the OS's turf, and it has the keys to absolutely everything, full privileged access. And that wall between them, that's what keeps your computer from falling apart. So we've got these two worlds, user mode and kernel mode, and there's a super strict wall between them. So how do we get across it safely? Well, we need an official, secure bridge, and that bridge has a name, the system call.
A system call is, well, it's exactly what it sounds like. It's your program making a formal, super well-defined call for help to the operating system. It's not trying to sneak past the guards or anything. It's ringing the front doorbell and politely asking the kernel, the one with all the power, to please perform a special task for it.
Okay, so here's how that whole handoff actually works. Your program needs to do something special, let's say read a file. To ask for that, it runs a special instruction that basically acts like a trap door. The CPU immediately shifts from user mode into the super powerful kernel mode. This hands control over to the OS, which goes and safely performs that file read. And once it's done, the CPU flips right back to user mode and gives the data back to your program, which can now just carry on its merry way.
So what kinds of things can a program actually ask for? Well, it turns out it's pretty much everything that makes a computer, well, a computer. Let's go ahead and take a look at the menu of options.
Now, this isn't just some boring list. This is basically the DNA of everything you do. Every time you double-click an icon to start a program, boom, that's a process control system call. When you hit save on a document, that's a whole bunch of file management calls, create, open, write. Sending something to your printer, that's device management. Heck, even just checking the time in the corner of your screen is an information maintenance call. They're happening all the time, thousands of times a second, completely under the hood. And you know what's really cool? While every modern OS does this, they don't all use the same names for things. It's kind of like ordering coffee. Whether you ask for a grande or a large, you're still getting a big coffee, right? On Windows, a program calls create process to get something new started. But on a Unix-based system like Linux or Mac OS, it calls fork. It's the same fundamental idea, just a different dialect. To really see this stuff in action, let's zoom in on one of the most famous, most powerful system calls ever, fork. This one little call is the main way new processes are born on systems like Linux and Mac OS. The idea behind fork is actually deceptively simple. When a process calls fork, the operating system creates a brand new process that's an almost perfect clone of the original. We call the original the parent, and the new one is the child. And then they both start running from the exact same spot in the code, the line right after that fork call. All right, little pop quiz for you. Take a look at this code. We've got a single call to fork, and then a command to print hello. Now remember, fork creates a clone, so you've got the original parent and the new child, and both of them are about to run that next line. What do you think? How many times is hello going to show up on the screen?
Twice. You got it. The parent prints and the child prints. Simple enough, right? But what happens if we do it again?
Now look at this. We call fork 2 times in a row. So the first call creates one child, which gives us a parent and a child. But then that second fork call gets run by both of those processes. So how many hellos do we get this time? 4 times. And this is where the magic happens. The first fork gives us a parent and child 1. Now, both of them run the second fork, so the parent creates child 2. But at the same time, child 1 creates its own clone, child 3. And just like that, you have 4 processes all ready to print hello. This is where you really see that explosive exponential growth. And this leads us to a really simple but incredibly powerful formula. The total number of processes you end up with is always 2 to the power of n, where n is just the number of times fork gets called. So if you had 3 calls, you'd get 2 to the power of 3. That's 8 processes. This isn't just a fun little trick. It's the core of how command line shells launch new tasks so efficiently. And hey, here's a little pro tip, maybe for an exam question. If you're asked for the number of newly created processes, so just the children, all you have to do is subtract 1 from the total. That gets rid of the original parent. It's a small detail, but it's the kind of thing that separates the pros from the rookies.
So we just went super deep on one specific call. But let's zoom back out to the big picture again. Why is this entire system of controlled access so absolutely essential to how our computers work?
You know, it really all boils down to this. System calls are the unsung heroes of computing. They act like a security guard, providing protection and making sure no program can mess with memory it doesn't own. They're like a translator, providing abstraction so developers can just say, write to this file, without needing to know all the messy hardware details. And ultimately, they provide the stability that stops one bad app from bringing your entire machine crashing down. This quote, it just says it all. There's no backdoor. There's no secret side entrance. If a program in user mode wants anything from the hardware or from the OS's core services, it has to go through the formal, secure, well-defined process of a system call. It is the one and the only way in. Okay, that was a lot of ground to cover. Let's take a second and just lock in the key takeaways from our little journey into the heart of the operating system. So to recap, we've learned that computers have a protected kernel mode for the OS and a limited user mode for our apps. We saw that system calls are the secure bridge between them, and they manage basically everything a computer does. We saw a powerful call like fork can create processes exponentially, and most importantly, we learned this whole system is the absolute bedrock of system stability and security. So I'm going to leave you with a final thought to chew on. What would our digital world even look like without system calls? Just imagine every app having to know the nitty-gritty details of your specific graphics card, your hard drive, your network adapter. It would be a world of total chaos. And it really makes you appreciate this invisible, elegant system that's working for us all the time. Thanks for watching The Explainer.